Hello. We're continuing our discussion here with looking at tangent and velocity problems, and we're going to focus on the second part, looking at the velocity problem. So what this problem says is we're wondering how we can find the velocity of an object at a point in time if we know the position during a period of time. Velocity, we want to remember, describes the rate of change of position with respect to time. So let me say a car analogy. Suppose we have an odometer and a clock. Can we create or have a way of determining a speedometer? So if you know how far you've gone and you're measuring the time along the way, can you figure out how fast you're going at an instant? That's the idea. So again, if you want to, you can think about the car analogy. Imagine you've got your odometer, your trip odometer, or whatever it is, and you have a clock in the car. Could you use that to figure out a speedometer if your speedometer was broken? So maybe that's a silly example, maybe not, but kind of a more tangible idea. All right, and that's our kind of just what we wanted to say here. Our more general question is, how can we find the rate of change at an instant? How can we find the velocity at a particular time? So the example here, just to start with, was suppose at 1 o'clock I'm 50 miles from home, so I'm driving in a car, let's say, and at 3 o'clock I'm 180 miles from home, and we've got other hypotheses there, like moving in a straight line, so on, but won't get too hung up on it. The question is, what was my average velocity during this time period? Well, that's a quick one to figure out. My change in distance over a change in time is what I want to compute. And that's 180 minus 50 over, so that's going to be in miles, and change in time was 2 hours, so that's 130 over 2, or 65, and that would be miles per hour. So that's my average velocity during that time period. But the type of answer, or the type of question we're really looking for with this velocity problem is, what was the velocity at? Oh no. There. At that particular time, and I just made up the time. There's nothing special about 138, but instead of over a period of time, what was it an instant? So again, odometer information, if you like, clock information. What's the speedometer information? So if we were able to plot position as a function of time, the velocity, or the instantaneous velocity, at a point in time corresponds to the slope of the tangent line to the corresponding point on the graph. That sounds familiar. Well, that's when we said the heading here. It's this tangent problem, velocity problem connection. Mathematically speaking, we're really talking about the same thing. Tangent problem is a little more abstract. We're just talking about curves and lines next to them. Velocity problem is a little bit more concrete, tangible. You're imagining a particle moving, and somehow we have a description of it, which maybe is a little far-fetched, but imagine a particle moving or a car moving or some object. But it turns out mathematically we're really just talking about the same thing. And here's the connection. So the average rate of change corresponds to the slope of the secant line, and the instantaneous rate of change corresponds to the slope of a tangent line. And what we have with this example, the tangent problem is the tangent problem. The velocity problem is a rate of change of position, but you can have any quantity and you can look at how it's changing. So it doesn't have to be velocity. It could be volume of something changing with respect to time, or it could be the surface area of an object with respect to the change in the height of some measurement. Or I don't know. There's a million things, and we'll look at them with different examples. But like I said, the example we have here, a real-world example, is for velocity. But this idea is true no matter what it is we're talking about. The rate of change of a quantity corresponds to the slope of the secant line if you've graphed, if you have a function that describes that quantity. And then the instantaneous rate of change with the tangent line. So if we were to think about this problem, and let's say we had time here and position here, and let's say I'm going along the way, I've driving in my car and I'm going kind of fast, and I'm going to slow down a little bit because I saw a cop behind the bushes or something, and I speed up again, and whatever it might be. Let's say it took me, well, let's just say what we had before, 130 miles. I traveled 130 miles, let's say it was 2 hours. So what we're trying to find then is not the average rate of change, which would be, in thinking about that connection with secants, the slope of that secant line. In fact, the slope here is the average velocity. But maybe I want to know what's happening at this particular time period. Think about that tangent line there. That slope would be my instantaneous velocity at that time. Maybe for just one more example, do a different color here. So it looks that slope is not as big, so my velocity at that time was less than my average velocity. Whereas something like this, looking at that tangent, looks like that. There's my instantaneous velocity at a different time period. Here, I'm driving a bit faster than I was in my overall average speed velocity, but I wasn't changing direction here. So that's what it is we're looking at. So we've got this velocity problem, and like we said, it's kind of a real world example, something you can think about, you have familiarity with, and we relate it to this tangent problem, which is a little bit perhaps more abstract. We're really talking about the same thing. So again, rates of change is what we're thinking about. An average rate of change would correspond to the slope of a secant line, and an instantaneous rate of change would correspond to the slope of a tangent line. So we know how to find the slope of a secant line. What we're doing with calculus, our earliest application that we're going to look at once we figure out how to describe this, is to come up with the slope of a tangent line.